Hello. Hello guys. Last class in last video I've discussed inductive effect and its types. Now I'm going to teach you the applications of inductive effect, which is very important from the point of competitive examination. Please, if you have not gone through the earlier video, please go through it. Now then you watch this video, you will understand. So in brief, I will explain you inductive effect, minus I effect. What you should remember is what are the electron donating groups and what are the electron withdrawing groups. Minus I effect is due to electron withdrawing groups and plus I effect is due to electron donating groups. Now when you come to the applications, okay, first we'll go for applications. Now first application is effect on bond lengths. How minus I effect is minus I effect decides the bond lengths. So you can not only minus I effect, inductive effect I can say. So I will take an example. I will explain through an example. CH3I, CH3Br, CH3Cl, CH3F. That is methyl iodide, methyl bromide, methyl chloride, and methyl fluoride. Now, here 4 different electronegative elements have been attached to the methyl group. That is fluorine, chlorine, bromine, and iodine. If you see the electronegativity of which of the halogen has most electron withdrawing property, that is the one which has most electronegative. The one which is most electronegative element that has the most electron withdrawing ability. So fluorine has the highest electronegativity than compared to chlorine, then compared to bromine, and then compared to iodine. Hence fluorine will withdraw this sigma electrons very strongly, and which gives negative charge on the fluorine and positive charge on the CH3. That is minus I effect is more in this case. So bond will be more polar due to more electronegative fluorine atom than chlorine, which shows less minus I effect than compared to fluorine, but compared to bromine it shows more minus I effect. So like this, from CH3I to CH3 fluorine, minus I effect increases. So as the minus I effect increases, bond length decreases. Minus I effect and bond length, they are inversely proportional. Now similarly dipole moment. Now similar example only will take CH3I, CH3Br, CH3Cl. The more the electronegative element attached to the carbon chain will induce more charge in the molecule. Now here Cl will give a negative charge, higher negative charge than compared to bromine. So the charge developed here is more, hence the polarization in this molecule is more than compared to CH3Br and CH3I. Hence dipole moment is also more where charge is more. So CH3Cl will have the highest dipole moment than compared to CH3Br and CH3I. Now the very important concept is acidic strength of carboxylic acids and phenols. Now I will take 2 examples. Here I have written, this is HCOOH, that is formic acid, and this is acetic acid. Okay, now both of the acids, they have hydrogen in them, right? So they have an ability to donate this hydrogen. So the one which donates hydrogen are called as acids. So when this formic acid donates this proton, okay, or when this acetic acid donates this proton, their structure becomes like this: HC double bond O minus, and H will come out as a H plus. Here also CH3 C double bond O minus, and H plus will come out. Now when you see this structure, okay, this is O minus. This can be written in its resonating structure. Minus will come here, this double pi bond will go here, HCO minus double bond O. Similarly here this minus come here and this double bond goes here, CH3C O and O minus. Now here one thing you should remember is which is the electron donating group. Here if you see formic acid and acetic acid, CH3 is a electron donating group. This CH3 donates electron here, right? Now if you see its resonance structure, if you see the resonance actual structure, this minus is relocalized over this 3 carbon atom. Hence here minus charge is there on this this carbon. If you see, there is some minus charge rotating through on this carbon atom. Here also there is a minus charge. Now hydrogen, it is not donor also, not acceptor also, so it has a no rule. So minus charge remains as it is. Here CH3 is a electron donor. Now here minus charge. So electron donor means what? Already there is an electron density on the carbon. So again, more upon that, this CH3 is also giving electrons to the carbon. So electron density on the carbon is increasing. because of that, what will happen? There is huge electron density here, hence this destabilizes. Suppose if I add fluorine, okay, for example, in case of CH3, if I take a fluorine, okay, just I am taking an example, okay, one electron withdrawing group. Now what this fluorine will do, here already electron density is there on the carbon. What is the nature of fluorine? Fluorine withdraws the electrons, right, towards itself. So this takes this whatever electron density is there, that stabilizes the electron density whatever present here. Hence what it will do, it will stabilize the carboxylate anion. If any electronegative element, suppose if here electronegative element, if you attach, it will stabilize the carboxylate anion and it will make it more acidic. So because of this CH2, because see, now in acetic acid, because of CH3's electron donating group, it will destabilize this carboxylate anion. Hence this carboxylate ion formation is bit difficult, okay, hence it will not lose that H easily. But whereas here in formic acid, this hydrogen, it will not stabilize also, destabilize also, but compared to acetic acid, this is more acidic, okay, here because CH3 destabilizes carboxylate anion, hence it will be less acidic. This is one application. See, electron withdrawing groups, here I can tell you, electron withdrawing groups or minus I effect decreases the negative charge on the carboxylate anion and thus the stabilizing it. So here CH3 is not decreasing the negative charge, instead it is increasing the negative charge. That means there is some tension, hence it is less acidic. Here it is not decreasing also, not increasing also, hence compared to this is more acidic. So here if you consider this one, acetic acid, fluoroacetic acid, difluoroacetic acid, trifluoroacetic acid, okay. Now how will you compare the acidic strength? In acetic acid, there is nothing to stabilize this carboxylate anion, but here there is one fluorine atom which is there. See, one fluorine atom is replaced by one hydrogen, hence that fluorine atom will stabilize the carboxylate anion. Hence the stability of carboxylate anion says the acidic strength of that molecule. Hence one fluorine will stabilize lesser, right? The effect of two fluorine atom will be more. Now when three fluorine atoms are present here, they will stabilize this carboxylate ion in more. Hence that trifluoroacetic acid will be more acidic in nature. This is third application. Okay, now if you come for the fourth application, now similarly the strength of phenols. Now how we decide the strength of phenols? Now strength of phenols increases, acidic strength of phenol increases when minus I groups are present on the ring. Here I have given three examples. One is paranitrophenol, phenol and paracresol. Okay, now if you see here, this three positions, okay, here nitro group is there, here hydrogen is there, here CH3 is there. CH3 is a alkyl group. Now nitro group is what? Electron withdrawing group. This is neutral. Then this is electron donating group. So if electron withdrawing group is present in para position or ortho position, the acidic strength will be more. Hence here nitro group is electron withdrawing group. So minus I group increases the acidic strength of phenol, whereas plus I group decreases the acidic strength of the phenol. Just remember this, okay. Now basic strength of amines. Now here we are comparing the basic strength of alkylamine, ammonia and arylamines. Now remember, what is a base? Acid is the one which donates the electron in case of phenol and this one, right, or carboxylic acid. But in case of amines, the base is the molecule, or the base is a compound which donates pair of electrons. Here nitrogen has a pair of electron, yes or no? The one which donates pair of electron is called as a base. Now here what is happening? Base means what? Electron density, donation of electrons. So CH3, what it does? CH3 donates electrons, right? CH3 is donating electrons. Here nothing is there, H is there, H and H2. So hydrogen, it is not come under electron donating also, electron withdrawing also, it will remain as it is. Whereas C6H5 is a non-donating group, okay, it will not donate electrons to the ammonia, NH2. So here CH3 is donating electrons to the NH2. See here, CH3 NH2. CH3 is donating electrons to the nitrogen. Hence already there is the electron density on the nitrogen. Now electron density will increase Okay, the electron density will increase because of this CH3. CH3 is also giving electrons. Hence, the electron density on the nitrogen of methylamine increases. So it can donate electrons easily, right? Now, if you say just ammonia, here H is there. H is not electron donating also, electron withdrawing also. So electron density will remain as it is. So it is not that strong as that of the methylamine. Whereas C6H5NH2, it will not at all take part in the, compared to this is electron withdrawing, you can say. Okay, so hence this will be less basic. So basic strength increases like this. You got it? If you have any doubts, you can give a comment. Okay, now very important is we also discuss the stability of carbocations and free radicals and carbanions. Now here you can see carbocation. Now plus charge means what? Plus charge is always refers to the electron deficiency. So how will you make this plus charge, this carbocation stable? When you attach an electron donating group, you will make it stable. Now you see here, plus charge means this carbon has some deficiency, which has a electron deficiency. You have to you have to overcome that deficiency. So for that you should attach electron donating groups. Now here how many electron donating groups are there? 3 groups are there, right? Electron donating groups are 3. Here there are 2 electron donating groups. In this case there is 1 electron donating group. Here there is no electron donating group. Here we write this as a methyl carbocation, primary carbocation, secondary carbocation, and this is tertiary carbocation. Now in methyl carbocation, this plus charge is not stabilized by any of the hydrogen, because hydrogen are not the electron donating groups. But in the case of primary, there is one CH3 group which is stabilizing, which is helping this carbocation to stabilize. But here there are two CH3 groups which are helping this carbocation to stabilize. Here there are three alkyl groups which are helping this carbocation to stabilize. So who will be more stable? So the one who has more supporters. So this carbocation has 3 supporters. So it will be stable with the help of this 3 alkyl group, whereas methyl group has no electron donors or no supporters. Hence it will be the most unstable carbocation. Similarly, free radicals also require electron donating groups. Here there are 3 electron donating groups which stabilize this radical. Similar explanation we are giving for free radicals also. Now whatever I have told you here, exactly reverse of carbanions. See here, in the case of carbanion, what happens is, now there is a negative charge. Okay, earlier we had a positive charge, now here negative charge. Now to decrease the negative charge, whom we require? We don't require now electron donating groups, we require electron withdrawing groups. Now the electron withdrawing groups, if present, they will stabilize, but when you add electron donating groups, they will destabilize, right? Now see, this carbon has already more electrons on them. Now again more upon that, this CH3, all 3 CH3s are giving excess of electrons on the carbon. So that is an overload of electrons on this carbon, right? So it will be unstable. Now if you see this, there are 2 CH3 groups which are donating electrons. Compared to this, here it is less, right? Only 2 alkyl groups are donating electrons. Hence the electron density on this carbon. Now what happens here is, here only 2 electron donating groups are there. Hence they will destabilize this negative charge. Even they will increase this negative charge on the carbon further. Now this CH3 will, here only one CH3 is there, so it will increase but less electron density. Here there is no electron donating groups, hence they will not increase the negative charge in the carbon. Hence this carbon is more stabilized as compared to these 3 structures. Hence methyl carbanion is more stable than the primary, than the secondary and tertiary. So these are the applications of inductive effect. In next video we will discuss about mesomeric effect and its application. Please, if you like the video, like it, share it, subscribe it, and thank you for the watching. Thank you.